Welcome my beloved viewers. So in this video we are going to be learning how to derive the Kepler's third law, law of harmonies. Now mathematically, the Kepler's third law can be written as the square of the orbital period, which is directly proportional to the cube of its semi-major axis. So this is what we are going to prove. So we are going to be looking at step-by-step process on how to prove this Kepler's third law. Step 1. So in step 1 here, we have the gravitational force between the sun and the planet. The gravitational force between the sun and the planet. So according to Newton's law of gravitational force, the gravitational force between the sun and the planet will be given as this expression. Okay, looking at this expression, we have the gravitational force will be the product of this, the mass of the sun, m subscript s, and the mass of the planet, all over divided by the square of the distance between them. G here is the universal gravitational force. So this is going to be our first expression. The gravitational force between the sun and the planet will be given as this. Now the next step, let's move to the next step. Okay, now the next step here, we have the centripetal force of the planet. So since the planet orbits around the sun in an elliptical orbit, it must experience a centripetal force, and the centripetal force is given as this expression, which is our second equation. This is given as mp here is the mass of the planet multiplying by the velocity of the planet, the square of the velocity, divided by the semi-major axis. Okay, equation 2. Now that is the second step. Now let's move to the third step, step 3. So here, step 3 says the gravitational force equals the centripetal force. When gravitational force equals centripetal force, what do we observe? Okay, let me share the board into 2. So here we have the gravitational force equals the centripetal force So what do we have? If gravitational force here equals centripetal force, we have gravitational force gravitational force equals centripetal force. So gravitational force is given as this, centripetal force is given as is on the right hand side of the equation. So what happens when we equate the gravitational force and the centripetal force? Okay, now at the left hand side of the equation we have the mass of the planet, which cancels out the other side of the equation, the mass of the planet in the other side of the equation. Also in the denominator at the right hand side we have the square of the distance. Okay, and at the right hand side we have r. So 1r here cancels the r squared. Now r cancel r squared, remain the r. So we will be left with this. We are going to be left with, when you finish the cancellation, we are going to be left with this expression. Okay, so we'll be left with this, which is going to be our equation 3. Equation 3. V squared equals to the product of universal gravitational constant and the mass of the sun all over r, which is the distance. So that is equation 3. Now let's move to the next step. Step 4. So step 4 here says what? The velocity of the orbit. The velocity of the orbit. So, but the velocity of the orbit of a planet is given as, of a planet in an elliptical or circular motion is given as 2 pi r all over t. 2 pi r over t. So in this equation here, so if v equals to 2 pi r over t, then v squared is going to be the square of this 2 pi r all over t squared. Okay, so, and as a result, when this expression is squared, you are going to be left with 4 pi squared r squared all over t squared. Now this is going to be our fourth equation, equation 4. Okay, which is the velocity of the orbit. Now the next step. Here, we are going to equate equation 3 equals to 4. We are going to be equating these velocities. So if equation 3 equals equation 4, we have what we have. We are going to have this. Okay, then if you equate equation 3 and equation 4 from the last expression, we are going to be left with this. We have this. Okay, so let's see. The next step here, we are going to cross multiply. Cross multiply. When you cross multiply, this here multiply this, and this guy here multiplies this. So when you cross multiply, what will you be left with? We'll be left with this here, this gm mass of the sun so when you cross multiply, you'll be left with g mass of the sun multiplied by the square of t equals to the 4 pi squared Okay, now in this expression now, when you make t, you want to make t squared the subject of the formula, we are going to divide both sides by the coefficient of the square of t. We divide both sides by this here. What are we going to be left with? So when you divide both sides by the coefficients of t squared, this cancel this, so there is nothing to be cancelled out in the right hand side of the equation. So we are going to be left with this. We are going to be left with t squared equals to 4 pi squared r squared all over r cube all over g mass of the sun. Okay, which is, let me put it out, is equation 5. Okay, so in this equation is going to be the last expression we are going to derive here. Okay, now this equation, now if you look at it very well, it resonates, or it implies the Kepler's third law. Now from this equation we can be able to say that therefore the square of t is directly proportional to the cube of r, which is the semi-major axis. So now, according to the Kepler's law, the square of the period is directly proportional to the cube of the semi-major axis of its orbit. Okay, so we are done with the proof. Proved. We are done proving the Kepler's third law of planetary motion. So therefore, from here we can deduce that t squared pi squared r cube all over mass of the sun. So when t squared is directly proportional to the r cube, therefore 4 pi squared all over gm here will be a constant, and this constant is for all planets. So I hope you find this video very useful. Make sure you click on the like and the subscription button. Thank you.